Okay, so we're continuing on talking about money. I think I looked at the recording because I forgot where the heck we were. But we were talking about, we had this example of if we invested $10,000 at age 25 and we, yeah, I know, it'd be nice. So that was if you got some inheritance from your grandparents. I don't know how likely that is, but and so what we did was we were looking at the accumulation over a period of 40 years as we reinvested our money into whatever investment we had. So those are examples of compound interest. There is something, I can't find the notes from last time, so I'm going to have to erase stuff as we go along. So there's, if you go back a step, there's something called simple interest. And simple interest, I don't think anybody really uses anymore, but I'm just going to explain what it is. Basically, it says you put some money in an account and you get interest, so much % interest per year, but you don't get any credit for the, say after 1 year, the money that you would get after that year, you don't get any credit for it. And so you only get interest on the original amount each year. So it turns out that the calculation is pretty simple. To calculate the interest for a simple interest account, the interest is the principal times the interest rate times the time in years. And remember, the one that we used the other day said that the amount was equal to the principal times 1 plus the interest rate to the t power, where t is the number of years. This is if it was done annually. And r is the interest rate, and p is the principal, which is the original amount you put in. So in this case, if you wrote an equivalent expression for simple interest, the amount would just be equal to P times 1 plus RT. So because you don't have the exponent, you don't get the benefit of each year getting credit for that amount you earn after each year. And so let's just look at let's just look at an example with the two cases, with and without compounding. This is with compounding, this is without compounding. So let's say we start off with $3,000. And our interest rate is 5%, which the decimal equivalent would be 0.05. And T is 4 years. So if you use simple interest, you would get the amount after 4 years is equal to the principal, $3,000, times 1 plus the decimal equivalent of the interest rate times the number of years. And to get my calculator, here's my calculator. So we'd have 1 plus 0.05 times 4, which is 1.2. So we have 3,000 times 1.2. So that is going to be $3,600. Now, if you compound annually, so we're saying compound annually, that means after 1 year that we take that interest for the 1 year and we put that in with our principal. The equation is that the amount after so many years is equal to the principal times 1 plus it's this top equation, the interest rate in decimal form raised to the fourth power. So let's see what that number is. It should be bigger. So we take 1.05 raised to the fourth power, and that comes out to be 1.2155, which is greater than 1.2. And so we get $3,646.52. So we get $46.52, which, you know, to start off with, doesn't seem like a huge amount of difference. You get $600 here in interest. Here you get $646.52. And you say, well, yeah, it's $52, and every dollar counts. But it's not like, wow, this is a huge difference. But if you do it over a 40-year period, there is a huge difference. That compounding makes a huge difference. Yes. $46.52. For you, it's the huge stuff. Yeah, that's right. So if you're Donald Trump, then that's not, you can't even think about that small amount. But for normal people, that's probably still $46.52. You can still buy something. What could you buy with $46.52? You could buy, well, we went to Alexandria over the weekend, and we stopped to get food. We stopped to have food for dinner. We stopped at Wendy's, and my wife and I spent $5.50 on our dinner. My wife had a cheeseburger, and I had a double stack and a bowl of chili. $5. That's pretty good. I felt proud. So that would buy me at least, that would be me about, what's that? Oh, for making the hamburger and stuff? No, I don't know. You don't think so? I always thought, like, if you price out a hamburger, it's actually, they're not huge profit on the hamburger, and there's more profit on the French fries and the drink. Is that true? Anybody work at a fast food place? Oh, don't tell me that. Okay. Okay. So continuing on. So the next thing we're going to talk about is we're going to, let me add, don't start writing all this stuff down here yet. I'm just going to add a page. So you can compound on a more frequent basis. You can compound semi-annual, which means twice a year, quarterly, which means 4 times a year, monthly, 12 times a year, daily, 365 days a year. And you know, nowadays, pretty much everybody does continuous compounding, but back when I was a kid, I had a savings account, and it would compound quarterly. So if you went to the bank every 3 months, they would write in, it was where they actually wrote in the numbers, and they would say, okay, you got this much interest, and your new balance is this. And then you go back 3 months later, and they would fill in the next. You mean it was ever all manually stuff? I mean, this is in the dark ages. But you know, nowadays, you tend to do everything continuously. But we'll explain. We'll explain the other. So what I want to do is I want to look at quarterly and daily, and then we'll go to continuous. So we want to compare how much different there is. So a previous case, we went from just simple interest, which is the least amount that you're going to get, to annually, compounding annually. So let's look at, let's do the same numbers, which I think were $3,000, 5%, 4 years. And I'm just going to write down annually because we just did that. And it was 3,600 and something. Does anybody wrote that down? 3,640, 46.52. Okay, so that was annually. So let's do quarterly. So the equation is slightly different for when you have, let me just copy this over so I'm just going to move it over here. So this is for periods other than, for less than a year. So let me just define what everything is. Well, everything's the same except N is the number of compounding periods. And N turns out to be equal to M, which I'll define in a second, times T, where T is the number of years. What M is compounding, whoops, there's Josh, compounding periods per year. So, you know, for quarterly, so we're doing quarterly up here. Quarterly, M is equal to 4. If it was monthly, M would be equal to 12. If it's daily, M was equal to 365. So this is the number of compounding periods per year. If you take that per year times the number of years, you get the total number of compounding periods. That's the exponent on the outside. R is still the interest rate, P is still the principal, A is still the amount after the finish. So let's go plug the numbers in. So for quarterly, we still have our $3,000 to start with. Then you have 1 plus the interest rate, which was 5%, 0.05, divided by, was it 0.05 or 6? I can't remember now. Did I? Make sure I did that right before we go any further. 5%, yeah, so we did 5%. Okay, let's see, where am I? Here I am. So that's the yearly interest rate. So what happens is when you divide by M, which in this case is 4, is that gives you the interest rate per period. So if you have 5% per year, then you have 1.25% per 3 months. If you did it monthly, you divide 5 by 12, and that would be that fraction would be the interest rate per month. So you take the yearly interest rate, divide by the number of compounding periods, which depends on what we call it here, and then you raise that to the 20th power, because N, which is the exponent, is the number of compounding periods times the number of years, which is 5, so you get 20. So now we just plug that into our calculator. This is when you need an exponent on your calculator, otherwise you're in trouble. So let's go ahead and calculate the number in the parentheses. So if you take 1 plus 0.05 divided by 4, you'll get 1.0125. So let me go ahead and do this in steps so you know what, if you're doing it on your calculator, you can make sure you're doing it correctly. So you get 1.0125. So this divided by 4 is 0.0125, and then you add it to 1, and you raise that to the 20th power. So 1.0125 raised to the 20th power is 1.28204. And multiplied by 3,000, and you get 3,000. Did I do something wrong here? Something seems wrong. Hold on a second. It's 4 years. Okay, that's my problem. Sorry. Let's fix that. So it's 4 years, so that should be the 16th power. That number was too big, so I thought I did something wrong. So, so that's to the 16th power. 4 times 4 years quarterly is the 16th power. Okay, so this whole thing's to the 16th power. So let's do that again. 1.0125 to the 16th power is 1.219989. Okay, then multiply it by 3,000, and you get $3,659.67. So let's compare that with our, when we do compounding annually, you get $3,646.52. So you're making about $13 more in 4 years by compounding it quarterly. So we're making progress here. But every time you compound more frequently, the return or the benefit kind of diminishes. So the final one is daily. So for daily, the difference is the number of compounding periods per year is 365 because there's 365 days per year. And N is 4, the number of years, times 365. So you get a big number to take the exponent. 4 times 365 is 1,460. But everything else remains the same. So the amount after 4 years compounding daily is going to be 3,000 times 1 plus the yearly interest rate divided by the number of compounding periods per year raised to the number of compounding periods total. And if we do this right, we should get a number very close to this, but slightly bigger. If it's way off, then something's wrong. So let's just do the stuff in the parentheses and then raise it. So it'll be 1 plus 0.05 divided by 365. You get 1.000136986. You raise that to the 1460th power, and the multiplying factor is 1.221386. And I'm carrying out a lot of decimal places because I want to make sure I have enough so I can get to the cents. So multiply by 3,000, and I get $3,664.16. Again, it's a little bit more. It's now $5 approximately. So going from yearly to quarterly, I get another $13 in 4 years. Going from quarterly to daily, I get another $4.50. So the next question was, what if you make it so the compounding period goes to an infinitesimally small value, and the number of compounding periods goes to a very big number? That's calculus. That's what calculus does. So we're just going to talk about the result, and this is just the example that I'm going to delete. So let me get far enough along here, and we'll skip over that for right now. We'll come back to that.
The attendance question for today is about credit scores. So I want you to go on Google, and I want you to search for the following. So here's what you put in. So just put in credit scores, Wikipedia, and then you'll see in the table of contents you can look at the United States, and in the first paragraph, I think at the end of the first paragraph, they'll list the 3 credit score agencies. I think that's spelled wrong. Agencies. Okay, so there are 3 main credit score companies. You might have heard of one in the news, Equifax. So that's one of them, and then there's 2 others. So that's your question.
There we go. So it turns out the formula for looks somewhat different. Instead of the amount, let me put this on one page. So, you know, for compounding that's not continuous, you take A is equal to P times 1 plus the interest rate divided by the number of periods per year which gives you the interest rate per period raised to the n power. So it takes on a different form. It uses this exponential result where e is just a number. It's 2.71828. So to introduce this letter E, which you may or may not have seen before, if you have your calculator, try calculating this: 1.00000001 raised to the how many zeros to have? I think it's the millionth power. Let's see if that's right or not. It's 1.000001 raised to the 1.000000. Yep. So did anybody do that? What do you get if you raise 1.00? I think I've got one extra zero in there. Remove one of these zeros. So it's 1.000001 raised to the millionth power. What you get is 2.71828. And if you let this go to 1.00 million zeros and then raise this to the appropriate power, you'll get, you get a more accurate result. So that's what E. This is E. And so in our equation, to calculate the amount after so many years, it's equal to the period times E to the RT, where in this case R is the interest rate again per year. And T is the number of years. If you have something less than, you can use decimal. I mean, they don't have to be integers. So if you did 2.5 years, you'd use 2.5. So for our particular example, we had $3,000. We multiply that times E to the interest rate, which was 5%, and we had 4 years. So that is 3,000 times this, and that's, if you have exponential on your calculator, E to the 0.05 times 4, which is 0.2, E to the 0.2 power is 1.221403. And if I multiply that out times 3,000, I'll get $3,664.21. So how does that compare with what I just got compounding daily? It's right down here. So it's $3,664.16 versus 21 cents. Okay, so I got 5 more cents. So there's not a whole lot of difference between compounding daily and compounding continuously. So why would they do that? Well, because the formula, it's a lot easier to apply this formula than it is to raise something to some huge value. So most of the time you have used continuous compounding. And it gives you the maximum possible amount that you can get through compounding. What the bank is not physically going in every 1/10 of a second and increasing your balance. All they do is they just give you this interest rate. This is the effective interest rate. So if you go in to get a CD at 5%, they'll say the APR, the annual percentage rate, or the APY, annual percentage yield, is not 6%. The yearly rate is 6%, but the annual percentage yield is 6 point something. It's a slightly larger value. That's effectively how much you're getting per year, because of this continuous compounding stuff. Okay, so that's continuous compounding. So those are formulas. They're pretty easy to use. Now, this effective annual yield, it's basically taking that formula for compounding of different compounding times per year and giving you the effective interest rate in a decimal number. So the equation is 1 plus the yearly interest rate divided by the number of compounding periods raised to the number of compounding periods minus 1. And if we look at this example of compounding quarterly with a 6% interest rate, the effective interest rate is going to be slightly larger than 6%. So we should get 6 point something. If we get 12, there's something wrong. So we'll just use the formula. So it's 1 plus the yearly interest rate in decimal form divided by the number of periods, it's quarterly, raised to the 4th power minus 1. So we get 0.06 divided by 4 is what? 0.06 divided by 4 is 0.015. So that's this divided out. Again, you can do it all at one time in your calculator, but I'm just going through this. So if you add these two numbers together, you get 1.015 raised to the 4th power, and 1.015 raised to the 4th power is 1.06136. And then we subtract 1 to get it in terms of the interest rate in decimal form. So the annual yield is 0.6136 or 6.136%. So when they advertise a yearly interest rate of 6%, because of quarterly compounding, you're effectively getting more than that. You're getting 6.136%. So you can expect after a year that that'll be your interest, not 6% of your balance, but 6.136. So it's what, a couple of percent, 0.13 out of 6. It's it's still money. And over a long period of time, even that small amount of interest can accumulate to a reasonable amount. It's not going to be the difference between retiring and not retiring, but it might be the difference between getting a nice car and a not so nice, a nicer car versus a nice car. So that's effective annual yield. So I think we've talked about everything in this section now. What you need to be able to do is to take a savings account balance with an interest rate and a period, number of years, plus some information about compounding, and use the formula to calculate the total amount after the contract, or whatever you want to call it. You can also should also be able to calculate the effective annual yield, and you should be able to also figure out how much you have if you continuously compound. Now I'm going to do an example here somewhere. Here it is, the TV commercial. I don't know if you guys have seen the TV commercial. They go out and they say, hey, how much money do you have in your wallet? So the guy opens his wallet and he goes, I got $42. So he says, do you think that's going to make any difference at your retirement? No, that's not very much. So I might as well spend it instead of putting it in the bank, because it's not even going to be worth putting it in there. And what they do is then say, well, if you put that amount per month into an account that gets a certain amount of interest, by the time you retire, it's a lot of money. It's a lot more money than you think it would be. So we're going to figure out how much, if you were 25 years old and you started putting $42 a month into an account, how much money would you have when you became 65? $42. That doesn't seem like, maybe it does. I mean, it does seem like a lot to you guys, but hopefully when you get a job, it might hurt a little bit, but it might not hurt so much that you could, if you knew what was going to happen with it, if you didn't think it was insignificant. $42 a month. That's only what? That's $1 a day. That's $1.50 a day, right? So if you bought didn't buy French fries or something like that, and you put that money in the bank instead of buying French fries. It'd be good for you in lots of ways because you'd save money and you wouldn't gain as much weight, and your arteries wouldn't become clogged. So now, what we've learned so far, the formulas don't apply to that. I'm not going to go through the formula that would apply, but I'm going to do it on a spreadsheet because a lot of the calculations that you could, to be able to predict things like retirement, how much money you're going to save, it's not rocket science. It's just a lot of repetitive calculations that are fairly simple. And so if you have a spreadsheet, you can do those calculations. I'm not going to expect you to be able to repeat what I'm doing, but hopefully you'll pay attention, so you'll say, oh yeah, that actually wasn't too bad. It's not really that hard a calculation. And I could do that myself. And I've done that, when I'm trying to figure out whether I have enough money to retire or how well I can retire, I pulled out a spreadsheet. And everybody can get a spreadsheet these days, as we know, using Google Sheets. So I'm going to go through it, not sort of a moderate pace here, just to show you. Okay. So what we're going to do is we're going to have a column that is the month out of those 20 years. So I'm going to do this for 20 years. And I'm going to have a column that is the balance of the account. And then I'm going to have a column that's the amount of interest that I gain every month. And I'm going to insert a couple of rows here so I can input the interest rate. See how that affects things. Interest rate, I'm going to use 6% just to start off with. That's a reasonable number to expect. And we're going to start at month 0. And how many months are there in 40 years? So there's a math problem. How many months are in 40 years? What's that? Yeah, which is 480. Yep. So we're going to have 480 months. So we'll go down to 480. So what this does is it just copies, just like we've done before. It just copies down the numbers one by one. So that's the numbers. Okay. Now, I'm going to say per month. Okay, we'll change that as well. So I'm going to put in 40. What was the number? 45 or so? What was it? $42. Okay, I think that's what the commercial says. $42 per month. Okay. And I'm going to say, I'm going to have a column here that's, what do I want to call it? Deposit. So that's how much I'm putting in each month. So each month I'm going to put in $42, but I'm going to, instead of writing in 42, I'm going to choose that cell, and I'm going to put a little dollar sign so that it doesn't change when I copy it. So I'll copy that. Well, I'm just going to copy it all the way to the bottom. I might have been able to do it all at one time, but it's easy just to copy. Okay. So I'm doing $42. Now, in reality, if you can afford $42 now, you're probably going to be able to afford more later, but this is kind of a minimal situation. Okay, so let's say the first month I put in $42. So the balance is going to be equal to the previous value, which is 0. So I'm going to say, actually, I'm just going to enter $42 right here. Okay. So first month, beginning of the first month, I put in $42. Now, at the end of that month, I'm going to get some interest on that $42. So the amount of interest is going to be equal to the balance from the previous month times the interest rate, which is 6%. But I have to convert that. Well, first I have to put the dollar sign so that it uses that number all the time. I'm going to divide by 100 to get a decimal, and I'm going to divide by 12 because I have 12 months. So that first month I get 21 cents of interest. So the end of the first month, my new balance is my old balance plus my interest rate, plus my interest, plus the amount that I stick in there the next month. So I add those three numbers together, the previous balance, the interest for the month, and the new deposit, and I get $84.21. Now I should be able to copy these formulas down all the way down, and it should work. So let's do this. So I'm just copying those values. They'll take the previous okay, so there we go. So you can see, at first, most of the increase in the balance is because I'm adding $42 every month. But notice that the interest rate, the interest that I'm earning every month is getting larger and larger and larger. And at some point, the amount that I get from interest becomes larger than $42. So after about, well, that'd be about 12 years, the amount of interest I'm getting per month is equal to the amount that I'm sticking in there. And you can see the balance is growing and growing and growing, so that for $42 a month for 40 years at 6% interest, well, what I'm going to do is I'm going to copy the number to the top so I don't have to keep looking at it. It's $84,000. Okay, so we're going to put that over here. So this is equal to cell B, 480, 484 maybe? Is that right? Yep. So that's my final balance. So what seemed insignificant, somewhat doable, $42 a month, $1.50 a day, after 40 years is $84,000, which is a nice, you'd like to have $84,000, I'm sure. Well, to get 6% interest rate, you probably would not. What the more likely scenario, the more logical scenario would not be to put it in the savings account, but to invest it in some kind of mutual fund, which would have a larger. Yeah, just go ahead and say it there. A larger return on investments, and you can do that. You can put it in small increments every month, because you're not personally buying the stock. You're buying kind of stock in this big pool of people that are buying the stock. So now, if 6% is a conservative number, but if you, and I wish I could say that it's going to be like this in the future, but if you go back to the 1900 and you look at the long-term growth of stocks, it's probably 11 to 13%, some number like that. So if I put 11% in there, so I put that money, because it's $42 every month, I just put it in there. I don't worry about it. I just put it in some kind of index fund, which means that I don't have to manage it, and I get 11% return instead of $84,000. I'll have $364,000 at the end of 40 years, which is pretty, that's pretty impressive. Now, if I put in, if I put in a large amount, $100, and again, $42 you might be able to afford when you're 25. You hopefully will be able to afford more as you go along, and you could reflect that in your spreadsheet. You could have your deposit increase by a certain percent every month, maybe tied to inflation or something like that. But if you say per month you've done $100 per month, then you'd have $863,000 after 40 years. Now, the reality of the situation, it's hard to know whether you could get 11%. And this isn't some kind of, we're not talking about buying some swampland in Florida. These are historical stock market index spread over a lot of different diversified over a lot of different industries and things like that. Now, if you put it in a CD where you get 2%, you only have $73,000. So it's a big difference between putting it in something that gets 11% and something that gets 2%. anyway, that's kind of how the whole thing works. So the moral of the story is try to come up with even a moderate amount of savings done over a very long period of time can result in a pretty decent amount at the end of your working career. So this is one example. We'll continue that. I'm encouraging you to try to save some money. You don't have to think I got to save $1,000 a month to make it work. You've got to be consistent about doing it, and you sometimes have to let it go as far as sometimes you have to invest in things that are not that they're unsafe, but they are a little more scary than you might want to admit. You might want to not do. So anyway, that's. Yeah, they say there's you should have a you should have some, and I think I can't remember exactly, but I think it's a couple of months' salary at least. Whatever you're living off of. So you have to be living independently. So you're talking about rent and car payments and whatever it is. And I think it's what is it called? There's a special name for it. It's not a rainy day fund, but it's an emergency fund. So they recommend that you have something. Well, we could look it up online. Let's just see what it is instead of just making this up. All these things nowadays you can find it, and again, be careful about where you go. You don't want to be reading fake news or fake investment advice. But yeah, so if I said how much money should I have in an emergency fund? There you go. So here it is. Financial experts are always saying you should have between 3 and 9 months of expenses saved in an emergency fund. Okay, great, but which is it? Yeah, so if you need $2,000 a month to live, there's a big difference between $6,000 and $18,000. I don't know what the answer is. I would look for something from somebody who's reputable, like Vanguard. That's a well-known investment fund. Yeah, so they're saying 3 to 6 months worth of living expenses. Yeah, and it talks about these kinds of things, and it says something is better than nothing. There's also a rule of thumb of how much money, and a lot of it depends upon whether you are, whether you have a pension, some kind of pension plan, which most people are not having these days, but I do have one I have a pension. I'm not collecting it. I have a pension from Midwest-Vaca that I'll get when I could start taking it when I'm 62, but I'll probably wait till I'm 65. And that's a reasonable amount of money. But I think if you don't have something like that, you just have Social Security, what I've seen is they say that you should have between 10 and 12 times your final average salary. So if I finish making $50,000 a year, I should have between $500,000 and $600,000 saved to maintain, because once you get Social Security, now because I have a pension, I don't need to have that much money. And we just saw that kind of number is not outside of the realm of possibilities. If you just consistently save. There's also the rule of thumb you should target about saving about 10% of your salary over the life of your working career. Now I have the Perry McClure students are listening to this recording later, and the teacher who's working with them She has a master's degree, so I'm interested to hear what she has to say because I get somebody else's. She'll email me and say, you're way off of that, so I'm interested to see if she agrees with what I say because she knows more about it than I do. We'll talk about credit score later when we talk about credit. Why you want to, what you need to do to get a reasonable credit score, why it's important. But the main thing coming out of this first chapter is, so there's your homework assignment, is that try to get in the habit of saving some money even as you are younger. Did I tell you my story about the GE stock that I got? Yeah. And personally, looking back, one of the mistakes I made early on, not that it was a fatal mistake, but I could have done better, is I was too conservative in where my money went that I invested from my personal through the company. What's that? Yeah, that's the idea. There are these things called target funds, which are, within the last 5 or 10 years. And what they do is they vary the amount of different kinds of investments depending upon your age. And when you're young and you have time to recover from dips in the stock market later on, they invest more in stocks and less in other types of more stable investments. And as you get close to retirement, they go more into cash and bonds, and it's safer, but not as high a return. So, as James said, when you're younger, you don't have to go crazy, but you might do like a S&P 500 index fund or NASDAQ index fund, which just means that they're buying a lot of stocks throughout the entire portfolio. So if one goes down, the other one will go up, and on average, that does usually about as good as somebody actually trying to actively manage funds. But yeah, don't be too. You don't have to put a huge amount in when you're young, but you also don't have to be too conservative. I was too conservative early on, and I could have done much better if I had that advice, which nobody gave me that advice. Well, yeah, you don't want to do something like that. Yeah, there's all kinds of stuff that you don't really want to get involved in unless you know what the heck you're doing. Okay, so the second section we're going to talk about is consumer credit. So we're going to talk about loans, installment loans, and credit card, how credit cards are the amount that you pay in interest. They talk about a kind of loan that I have, and this is, Carol, you're going to have to help me out here when you watch this. I couldn't find any real examples of this. It's a simple calculation, but I don't know if it really has any much practical value. I'm going to just mention it because it's in the book, but and there will be some homework problems, but I'm just telling you take this with a grain of salt. So there are what are called add-on loans, and basically what an add-on loan is they don't give you any credit for paying installments. So you would basically pay the same amount of interest whether you waited the entire length of the loan and then paid it all off at one time, or if you paid it off in installment loans. So the way the payments are calculated is they calculate the total amount you have to pay back, assuming you're not getting any credit for paying it early, and then taking that total amount and dividing by whatever frequency of the payments, which is usually monthly. So I'm just going to give you an example of how that would be done. Again, I tried to find somebody who actually did what's called an add-on loan, but I haven't found it yet. So let's say you borrow, we'll assume it's some shady furniture dealer or something. So let's say you borrow $2,000 to buy furniture. The loan is 4% interest, and we're going to, the length, the term of the loan is 3 years. And the question is, what is the monthly payment? Question mark. So the way you do it is you basically figure out how much you need to repay. So we'll call that A. The amount to repay is the principal, which is the amount you borrow, times 1 plus the interest rate times the number of years. And there's no exponential thing here, so it doesn't give you credit. Well, it doesn't give you credit for paying off in monthly installments. It just spreads out the cost over the period of the loan. So the amount that you have to pay back is going to be equal to $2,000, which is the amount. I'm using this formula right here, times 1 plus the interest rate in decimal form, so it's 0.04 times 3 years. So it says if I borrow $2,000 for 3 years, this is how much I have to pay back after 3 years. So it would be 1 plus 0.04 times 3. So the term in the parentheses is 1.12. So multiply 2,000 times 1.12, and we get $2,240. So I'm paying $2,000 plus $240 interest. Now the payment, the way these add-on loan payments would be calculated is you just take the amount that you owe after 3 years and you divide by the number of months. So that would be T is the number of years times 12. 12 times T would give you the number of months. So for our case, we owe $2,240 and we have 36 months because it's a three-year loan. And so we take $2,240 divided by 36, and our payment would be $62.22 per month. So if you multiply that by 36, you pay the total amount. But the problem here with this kind of method is you pay $62.22 the first month, and you're still having to pay on the total amount, the $2,000. So you're not getting any credit for that. I think in the old days, before calculators and other things, it was an easy way to calculate payments, but because it's so easy to calculate an installment loan, which is like car payments or house payments or anything, I think these days, you wouldn't actually do an add-on loan. But I have now demonstrated, I feel vindicated that I have covered that material. So what I'm going to do now is talk about installment loans, which is pretty much what everything is these days. So if you buy a car, how do they figure out what your monthly payment is? Based on how much you're borrowing and the term of the loan and the interest rate. So I'm going to show you online how you would do this, because that's what you would do in the future. Then I'm going to demonstrate how the calculation is done, which is, again, a simple calculation. It's just done over and over and over again. So we're going to use a spreadsheet for that. So we're going to switch back over into the internet. So I'm just going to go to Google. And all you have to do is look up loan calculator. It doesn't matter what kind of loan it is because they're all the same. Whether it's a mortgage or whether it's a car, same calculation, just more money for a house. So this is bankrate.com, which is reputable. And the things you have to input into calculating your monthly payment is how much you're going to borrow. So I'm going to say I want to borrow $20,000 for my car. I'm not a spendthrift, so, and it's how long the loan's going to be. You can either do it in months or years. 5 years is 60 months. So I'm going to say 6 years. And the final piece of information is your interest rate. So I'm going to say 6.5%, 6.5%, and then you say calculate. And what do you get? $336.20. So that's, and of that $336.20 over the entire period of the loan, 82.62% of that is paying off the $20,000, and 17.38% is paying the interest on the loan. But you don't pay, the interest is more at the beginning of the loan and less at the end of the loan, which we'll demonstrate here. So besides figuring out your monthly payment, if you go down, it says show amortization schedule. It's a big word. Basically just shows you how your balance, how much you still owe on the car varies with time. So if you said after a year I want to pay the loan off, you'd know what that value is. So we do that. It says show amortization schedule, and what you'll see is like a spreadsheet. So in March of 2017, which is this month, we owe $20,000. Now after 1 month, the way it works is you make a payment of $336.20 for that month on $20,000 at 6.5% interest. The interest for that month is $108.33. So your payment is more than your interest. So that means you have this extra amount. That extra amount goes to paying off your balance. The add-on loan didn't do that. It didn't reduce your balance. So this is giving you credit for reducing the balance. So the next month, you have the same payment, but because the balance is less than the original $20,000, your interest is less. It's about $1.23. So that extra $1.23 goes into your principal. And then you use that principal to pay down the balance. And so what's happening is the balance is going down, so your interest is going down, which means that your payment is going up, your principal is going up, and each month you're paying more, you're contributing more of your payment to paying off your balance. So after a year, you've got, you still owe a lot of money, but it goes quicker as you get further into your loan. So that's the whole idea behind installment loans. And whether you're buying a car or whether a house or whether probably furniture or anything, they should give you credit for paying off the balance, reducing the balance. So that's easy, right? Anybody can do that. You just have to put in your initial loan amount. So if you go to buy a car and you figure, because a lot of times when you go to buy a car, what's the first question they ask you? Probably most people haven't bought a car. They'll say, well, what monthly payment can you afford? So they want to sell you as much as they can, and then they back out which car you can do. But a lot of times the monthly payment is not just paying off the loan, it's other stuff that they may add in that you really don't need. I never buy anything extra when I buy a car, like a extended warranty and those things, because they typically, if they're pushing it, it's probably better for them, right? It's good for them if they're trying to sell it. And also because it also depends upon, how much savings you have in reserve. I'm old enough that I've got a lot of savings, so if I have to pay a little extra to get it fixed, over the long run, it's worth it me not to pay that extra amount. So you really want to go in knowing, go to your bank or some bank, find out what, is a reasonable interest rate, figure out how much the car you want to pay for the car, and figure out what your payment would be. And that's, you wouldn't really, it's better not to say what payment. Well, say, well, what cars do you have for this price? And you can figure out previously before you go in what kind of payment is associated with a certain kind of car. Okay, so let's show you how this calculation is done. It's pretty simple. This you are going to be responsible for, and there's some homework problems that go through this. So typically what I do is I just ask you to do the first couple of parts of the table. So let's see, I always forget how many rows I need here, columns. I need 6 columns. And I'm not going to do it in a spreadsheet, I'm just going to do it in a table first. So we can make sure we don't get too fast and we can follow everything. So this is, we're going to make our own amortization schedule here. Well, I'm just going to try to erase that thing, but okay. So the first one is the month. Let me put this on one page. So you got the month, you've got the payment, you've got what was the next one? I think it was the principal. Let me see, principal, yeah. You've got the interest. I'm missing something. What am I missing here? Oh, total interest. The total interest is just the total amount of interest you pay as you go through the loan. And then you've got your balance. That's how much you still owe. So let's say we're in month 0 here, month 1, month 2, month 3, month 4. So the first month you have a balance of, let's say it's $20,000, just like we did. So our conditions are the loan's for $20,000. It was 6.5% interest, and we had 7 years, 6 years, I forget. 6 years. We're not going to go out to 6 years, but we're going to start this thing. So after 1 month, you have interest. So the first thing you do is you calculate the interest. So this is month 1. Month 0 is just coming up with the balance. Okay, for month 1, the first thing you do is calculate the interest. So the interest per month is the balance, the total balance, times the interest rate, which is 0.065, divided by 12. So you use your monthly interest rate. So let's calculate that. 20,000 times 0.065 divided by 12. So we get an interest of $108.33. So we enter that here, interest, $108.33. And our payment was wrong button. What's the payment? $336.20. $336.20. So the next thing we can do is we calculate the principal, which is the amount the difference between the payment and the interest. So that's $227.87. So that goes right here. So let me make that a different color, just so it's 227.87. So that goes here, 227.87. My total interest right now is just the amount that I just put in there. It's $108.33. And then the final thing is you update the balance. So the balance is your old balance, which is $20,000, subtracting your principal, which is the amount that was part of the payment, which was more than the interest, and that difference gives you your new balance. which is $19,772.13. So that goes right here, $19,772.13. And then you just start over again. So we'll do 2 months worth by hand. So I'm going to move this month one down so I can keep everything in view. Okay, so now we go to month 2. So again, you start off with the interest. Again, you use the new balance of $19,772.13. You multiply by the interest rate, the yearly interest rate, divided by 12, which gives you the monthly interest rate. And I get $107.10. So that's my new interest, $107.10, which is less than I paid the first month because my balance is less. The next thing I do, my payment's still $336. So my next thing I do is the principal. That's the amount, the difference between the payment and the interest, which is now a little bit more. So I get $229.10. So that goes right here, $229.10. And then my balance, I take that principal and the old principal from the previous month, and I subtract the principal that I accumulated there, and that gives me, and my new balance is $19,543.03. $19,543.03. And finally, the total interest is I take the interest from the previous month and add. So I'm just adding these two together. So I get 108.33 plus 107.1, and that is 215.43. So you can see the rest of the thing is just repeating it over again, and that's why spreadsheets are the way to go with this. But I just want you to be able to do the first couple of months so you understand the mechanics. They're just simple multiplication, division, and subtraction. And if I compare that with my table, you'll see I've got after 2 months I've got 19,543.04. And here I've got 19,533.03. I don't know why I got a cent difference. I got that the other day too. So there's some rounding difference, but you mean change these payments? Yeah, you could do it. Yeah, you could do it in a spreadsheet. The online one would assume that it's always going to be the same amount. So that's a good point. So you could pay it off. You always have to pay at least the payment. You could pay more. What that does is it just pays the loan off earlier. We did that with our house payment. We ended up paying more than we needed to. So it just got paid off early, and there was no penalty for early payment. So if you can afford it, then what that ultimately does. Pardon me? All right, just pay off some of your debt like that. Yeah. Okay, so that's pretty much it for installment loans, whether your car payments or you're talking about house payments. They all stay the same. The next thing we're going to talk about is credit cards and how they determine what your interest payment is. The main thing about credit cards is they use what's called the average daily balance to determine what the interest per month is, or per, it's updated pretty much continuously, and they use more like a daily interest rate instead of a monthly interest rate. So we'll do that next time. So we've assigned section 1. We'll wait to do section 2 next time for assigning the homework.